Out beyond every star you have ever seen, there is a faint glow left over from the birth of everything. And inside that glow, scientists have found something that should not be there. A cold patch the size of 1 billion galaxies, rings that look like echoes, alignments that mirror our own solar system. Signals older than the universe is supposed to be. You and I are about to walk through the evidence. A wall of galaxies too vast to exist. A flow of clusters drifting towards something outside reality. A scar that may belong to a universe before ours. If this kind of cosmic detective work hits the right nerve for you, hit subscribe so you do not miss what comes next. Because the deeper we look, the clearer one's suspicion becomes. Something was here first. Every direction you point a radio telescope, you hear the same faint hiss. It is older than the stars, older than the galaxies, older than atoms. That hiss is light, the oldest light in existence. It has been traveling for 13.8 billion years, and it is still arriving at Earth right now, passing through your body as you breathe. Astronomers call it the cosmic microwave background. Think of it as a fossil photograph of the universe when it was only 380,000 years old. Before that moment, the cosmos was a thick fog of plasma, too hot and too dense for light to move freely. When that fog finally cooled, the trapped light burst outward in every direction. We are still inside that flash. Here is what should disturb you. That ancient light is almost perfectly smooth. The temperature reads about minus 454 degrees Fahrenheit, and it is the same in every direction to 1 part in 100,000. That smoothness is the foundation of modern cosmology. It tells us the early universe was calm, even, and uniform. Almost. Buried inside that smoothness are tiny ripples. Microscopic warm and cold patches scattered across the sky. For decades, scientists treated those ripples as the beautiful seeds of everything we see today. Galaxies grew from them. Stars grew from them. So did we. But starting in 2003, when the WMAP satellite mapped the sky in fine detail, the picture changed. And when the European Planck mission released its sharper map in 2013, the change became impossible to ignore. The ripples were not random. Some patches were too cold, some were too large. Some lined up in patterns that the standard model of cosmology cannot easily explain. One feature is so unusual that researchers gave it a name, the cold spot. Another is called the axis of evil, because it appears to point in a direction the universe should have no reason to choose. These features have been checked, rechecked, and confirmed by independent missions using independent instruments. They are real. The disagreement is about what causes them. Some scientists argue the patterns are statistical accidents. Strange, but possible. Others argue they are signatures of physics we have not discovered yet. A small group goes further. They suggest the patterns may be marks left by something that existed before our universe began. That last possibility sounds wild. It is also taken seriously by mainstream physicists, including a Nobel laureate. We will get to him in a few chapters. For now, hold on to one fact. The cosmic microwave background is the closest thing we have to a baby photo of reality. Every galaxy, every atom, every memory you have ever formed traces back to the moment that light escaped. And inside that photo, there are fingerprints that do not seem to belong to anyone we know. The first fingerprint is the strangest of all. It sits in the southern sky, in the constellation Eridanus. It is colder than it should be, larger than it should be, and emptier than it should be. Standard models give it less than a 2% chance of forming naturally. It has a name, and it has been watching us since long before we learned to look. In 2004, a team analyzing the WMAP data found a region of the sky that did not fit. They expected small fluctuations everywhere. What they found in the constellation Eridanus was a hole, a cold hole. The cold spot is a circular region roughly 1.8 billion light-years across. The temperature inside it dips about 70 microkelvin below the average. That number sounds tiny, but in the language of the cosmic microwave background, it is enormous. It is the largest single anomaly in the entire sky. To picture the scale, imagine the observable universe as a beach ball. The cold spot would be a discolored patch the size of a golf ball pressed into the surface, small in proportion, but visibly wrong. Standard cosmology has trouble producing a feature this big and this cold. Statistical models give it a probability somewhere between 1 in 50 and 1 in 200, depending on how you measure. That is rare enough to demand an explanation, but not rare enough to call impossible. So the hunt began. The first idea was simple. If there is a giant empty region of space between us and that patch, the light passing through it would lose energy. Empty space stretches as the universe expands, and photons crossing a vast void would arrive slightly cooler. The technical name is the late integrated Sachs-Wolf effect. The plain version is this. A long tunnel of nothing acts like a cold filter. In 2015, astronomers using survey data found something promising. A supervoid. A region nearly 2 billion light-years wide, with far fewer galaxies than expected, sitting roughly in the right direction. For a while, it looked like the mystery was solved. It was not. When researchers ran the numbers, the supervoid only accounted for a small fraction of the temperature drop. The cold spot is still colder than the supervoid alone can explain. Something else is contributing, and nobody is sure what. This is where the theories get interesting. One proposal suggests the cold spot is a bruise, specifically a collision mark left behind when our universe brushed against another universe in its earliest moments. According to some versions of the multiverse, our cosmos is one bubble among countless others. If two bubbles touch during inflation, the impact would leave a circular cold imprint on the sky. A circular cold imprint roughly 1.8 billion light-years across. Other physicists argue for more conservative explanations. Perhaps a rare statistical fluke. Perhaps an unknown property of dark energy. Perhaps a defect in the fabric of space called a cosmic texture, formed when the early universe cooled and froze into different states the way ice cracks across a pond. What unites every serious explanation is this. The cold spot is real, it is not a flaw in the data. It has been confirmed by Planck, by ground-based telescopes, and by independent analyses. Something carved a hollow into the oldest light we can see, and we still do not know what. The cold spot would be strange enough on its own. It is not on its own. There is a second feature in the cosmic microwave background that is harder to explain and harder to ignore. It does not just sit in one place, it cuts across the entire sky, and it points, somehow, directly at us. The cosmic microwave background should have no preferred direction. The early universe was hot, dense, and chaotic. After 13.8 billion years of expansion, any leftover patterns should be scattered across the sky at random angles. In 2005, two cosmologists named Kate Land and João Magejo looked at the WMAP data and realized that was not what they were seeing. The largest temperature ripples in the cosmic microwave background appeared to be aligned. The biggest patterns lined up with each other. And worse, they lined up with something local. They lined up with the plane of our solar system. The team gave the alignment a darkly humorous name, the axis of evil. The name stuck because the implication is genuinely unsettling. Either the largest features in the universe are mysteriously connected to the orientation of our tiny planetary disk, or there is a flaw in our understanding of the early cosmos so deep that we have not yet caught it. There is no obvious way for those two things to be related. The solar system is 4.6 billion years old. The cosmic microwave background is more than 13 billion years old. The patterns in the ancient light were imprinted long before Earth, the Sun, or any planet existed. So why do they appear to point our way? Three possibilities have dominated the debate. The first is contamination. Maybe the alignment is not real, maybe dust in our galaxy or radiation from the solar system, is leaking into the data and creating a fake pattern. This was the leading hope for years. Researchers carefully subtracted every known local source. They cross-checked WMAP results with the European Planck mission, which used different instruments, different orbits, and different analysis pipelines. The alignment survived. The second possibility is statistical accident. With a sky full of patterns, occasional coincidences happen. The probability of this particular alignment occurring by chance has been estimated at less than 1 in 1,000. Rare, but not impossible. Many cosmologists still favor this explanation because the alternatives are uncomfortable. The third possibility is the uncomfortable one. The universe really does have a preferred axis, and our model of cosmology is missing something fundamental. The standard picture assumes the cosmos is the same in every direction. If the axis of evil is real, that assumption breaks. A broken assumption at this level changes everything downstream. Estimates of the universe's age, calculations of dark energy, the size of the observable cosmos. None of these would survive untouched. There is also a fourth idea, quieter and stranger. Some theorists propose the alignment is a memory, a faint imprint from whatever set the initial conditions of our universe. If something existed before the Big Bang and left a directional bias behind, that bias could still be visible today, frozen into the oldest light. That is speculation, not consensus. But the speculation comes from serious physicists working with serious math. The honest summary is this: we do not know why the largest patterns in the sky line up with our solar system. The data is real. The alignment has been confirmed by multiple missions. The explanation is missing. And the axis of evil is not the only directional problem in the cosmic microwave background. There is another one. It does not just affect the largest patterns, it splits the entire sky in half. One side is hotter than the other, and no one can tell us why. Cut the sky in half and the two halves should look the same. That is the rule, the cosmic principle. The early universe was so hot, so dense and so well mixed that any large patch of sky should match any other large patch within a tiny statistical margin. North and south, east and west, same texture, same average temperature, same story. The Planck satellite checked, and the rule broke. When researchers split the cosmic microwave background along a specific line, the two hemispheres looked different. One side was slightly hotter, the other was slightly cooler. The fluctuations on one side were a little stronger. On the other side, a little weaker. The effect is small, about a 7% difference in the strength of the temperature variations. In daily life, 7% is invisible. In cosmology, it is a 5-alarm fire. A 7% asymmetry across the entire sky should not exist in a universe that started smooth. Inflation, the leading theory of how the cosmos expanded in its first moments, predicts almost perfect symmetry. Every reliable model says the two hemispheres should match. They do not. This is called the hemispherical power asymmetry. The plain version is simpler. Half the sky is louder than the other half. When the asymmetry first showed up in WMAP data, most cosmologists assumed it was a glitch. Maybe an instrument problem. Maybe a calibration error. Maybe leftover heat from the satellite itself. Then Planck launched a new mission, new instruments, new software, years of independent observation. Planck saw the same asymmetry, in the same direction, with the same strength. The glitch theory died. So what is causing it? Some physicists argue for a process called pre-inflationary anisotropy. The phrase is dense, but the idea is straightforward. Whatever existed before our universe inflated may not have been perfectly uniform. If there was a small lopsided feature in the seed state of reality, inflation would stretch that feature to cosmic size. We would still see the imprint today, baked into the oldest light. Other theorists suggest the asymmetry comes from a rare type of inflationary model where the expansion happened slightly differently in different directions. The math works. The physics is allowed. The catch is that no one can yet point to a clean mechanism that produces exactly the pattern Planck recorded. The most uncomfortable proposal is the simplest. The universe is not the same in every direction. The smoothness we built modern cosmology on is approximate, not exact. There is a structure to the cosmos at the largest scales that we have not yet understood, and that structure was set before the first second of expansion. A structure that old has only a few possible sources. It might come from quantum effects in inflation that we do not yet model correctly. It might come from a defect frozen into space when the universe cooled. Or it might come from something further back, something earlier than inflation itself. Notice the pattern building, the cold spot, the axis of evil, the hemisphere problem. 3 independent anomalies, each pointing toward a universe that carries directional information from a time before the Big Bang. That is the thread we are now following. And it leads next to a stranger possibility. What if the cold spot is not a bruise from another universe at all? What if it is a tunnel, a real tunnel, made of nothing, opening through the cosmos itself? In 2015, a team led by astronomer Istvan Sapudi made an announcement that sounded like science fiction. They had found, in the same direction as the cold spot, the largest known structure in the universe, not a galaxy, not a cluster, an emptiness, a supervoid, roughly 1.8 billion light-years across, a region of space containing far fewer galaxies than statistics demand. A hollow in the cosmic web large enough to swallow 10,000 Milky Ways and still have room left over. The discovery looked, at first, like a clean answer to the cold spot mystery. If a photon of cosmic microwave background light passes through a vast region of nothing, it loses a small amount of energy. Empty space is not truly empty. It expands. As it expands during the photon's crossing, the photon stretches with it and arrives slightly cooler than it left. A supervoid in the right place would produce a cold patch in the right place. The numbers seemed to match. The story seemed to close. It did not close. When cosmologists ran detailed simulations, the supervoid could only account for around 10% of the observed temperature drop. The cold spot is far colder than the void alone can explain. Something else is cooling that region. The supervoid is real, but it is not the full answer. It is a piece of a larger puzzle. This is where the physics gets stranger. A supervoid that big should not even exist according to standard cosmology. The cosmic web of galaxies grew slowly over billions of years from the tiny ripples we discussed earlier. Models predict voids, but voids of that scale are statistically rare. To find one in exactly the direction needed to partially explain the cold spot, sitting in our cosmic neighborhood is itself a small miracle. So we have 2 unlikely things happening together. A coldest known patch of sky and a largest known empty region, lined up in the same direction, neither fully explained. Some researchers argue this stacking is not coincidence. They suggest the supervoid and the cold spot are 2 visible faces of the same underlying event. A single deep disturbance from the early universe carved both features at once. The void is the structural scar. The temperature drop is the optical scar. Different signals from one source. What kind of event could carve both? The leading exotic answer is the bubble collision idea. If our universe is one of many bubbles forming inside a larger inflating space, 2 bubbles could meet in their earliest moments. Where they touched, energy and matter would be redistributed in unusual ways. Billions of years later, an observer inside one of those bubbles would see a circular region with an unusual temperature and unusual density. Cold, empty, round, aligned in a specific direction. That description fits the cold spot and the supervoid almost perfectly. This is not proven. It may never be proven. The bubble collision model makes specific predictions about polarization patterns inside the cold spot that future missions, like the proposed Lightbird satellite, will be able to test. If those predictions hold, the case for a real cosmic neighbor strengthens significantly. For now, the supervoid hypothesis tells us this. There is something genuinely large, genuinely empty, and genuinely strange sitting in the direction of the cold spot. It is not a mistake. It is data. And it may not be the only mark left behind. Because one of the most respected physicists alive thinks he has found something else hiding in the cosmic microwave background. Not a single spot. Not a single void. Circles. Concentric rings. Echoes of a universe that ended before ours began. Roger Penrose won the Nobel Prize in Physics in 2020 for his work on black holes. He is not a fringe figure. He is not a conspiracy theorist. He is one of the most influential mathematical physicists of the last century, and Stephen Hawking's longtime collaborator. In 2010, Penrose announced he had found something inside the cosmic microwave background that nobody else had been looking for. Concentric circles, faint rings of slightly varied temperature, nested inside one another like ripples in a frozen pond. To Penrose, these rings were not random noise. They were signatures, echoes left over from events that happened in a universe before ours. To understand why he made this claim, you need to understand the model he was working with. Penrose calls it conformal cyclic cosmology. We will explore the full theory in the next chapter. For now, hold on to one image. Imagine the universe expanding forever, growing colder, emptier, and quieter, until every star has died and every black hole has evaporated. Once nothing is left but radiation, there is no longer any meaningful sense of size or time. The end of one universe becomes the beginning of the next. If that picture is right, then events from the previous universe could leave imprints that survived the transition. Specifically, the gravitational waves from supermassive black hole collisions in the previous cosmos would imprint circular patterns on the cosmic microwave background of the current one. Concentric rings, centered on the points where those ancient collisions occurred. In 2010, Penrose and physicist Vahe Ghazardian published a paper claiming exactly this signal had been detected in WMAP data. They identified rings of unusually low temperature variance, nested in places where their model predicted they should be. The reaction from the cosmology community was sharp. Several teams reanalyzed the data and concluded the rings were consistent with random noise. They argued Penrose and Ghazardian had not properly accounted for statistical flukes that naturally produce circular-looking features. Penrose did not back down. In 2020, he and a new team published a follow-up paper analyzing Planck data. They focused on what they called Hawking points, localized hotspots in the sky that, in their model, are the final flashes of supermassive black holes from the previous universe, finishing their long evaporation. We will return to these in 2 chapters. The debate continues. Most cosmologists remain skeptical. A determined minority, including a Nobel laureate, argue the signals are real. Here is what makes this debate worth taking seriously, even if Penrose turns out to be wrong. The rings he's looking for are exactly the kind of signal that could distinguish one model of cosmic origin from another. They are testable. They are specific. They make the question of what came before the Big Bang an empirical question, not a philosophical one. For most of human history, asking what existed before the universe was a religious question. Then it became a metaphysical question. Now, because of patterns in the cosmic microwave background and the math of physicists like Penrose, it is starting to become a scientific question. We can look at the oldest light we can see, we can analyze it, we can compare it to predictions, we can ask whether the rings are there. That is a remarkable shift. And it raises the obvious next question. What is conformal cyclic cosmology actually saying? What does it mean for a universe to end and begin again? And how can a process that destroys everything still leave a fingerprint behind? Imagine a universe so old that every star has burned out, every black hole has evaporated, every atom has decayed. There is no matter left, only radiation, traveling forever through empty space. In that final state, something strange happens. Without matter, there are no clocks. Without clocks, there is no meaningful sense of time. Without massive objects, there is no meaningful sense of size. The universe at its end becomes, in mathematical terms, indistinguishable from the universe at its beginning. A featureless, smooth, radiation-filled state. That is the seed of Roger Penrose's idea. He calls it conformal cyclic cosmology. Each cycle is called an aeon. The end of one aeon, he argues, becomes the Big Bang of the next. The physics term that does the work here is conformal symmetry. The plain version is this. If you cannot tell big from small, and you cannot tell early from late, then the death of a universe and the birth of a universe become the same kind of state. One naturally flows into the other. Penrose's model does not require a singularity. It does not require a void. It does not require a creator. It requires only that the universe expand long enough, become smooth enough, and lose track of its own scale. After that, a new aeon begins automatically. This is radically different from the standard picture. In the standard picture, the Big Bang was the absolute beginning. Time started. Space started. There was no before because there was no time in which a before could exist. Asking what came earlier is like asking what is north of the North Pole. Penrose answers the question anyway. Something came earlier. Another universe, with its own galaxies, its own stars, its own black holes, its own civilizations perhaps. That universe ran its full course, expanded into emptiness, and handed the baton to ours. The transition is not a collision. It is not a bounce. It is a kind of mathematical handshake. The infinite future of one cosmos becomes the dense beginning of another. The total amount of structure resets. The total amount of memory does not entirely. That last point is where the model becomes testable. Penrose argues that during the previous aeon, supermassive black holes spent unimaginable amounts of time merging, growing, and finally evaporating through Hawking radiation. Each of those events releases energy. Each of those energy releases, he claims, imprints a circular pattern that carries through the handshake into the next aeon. The cosmic microwave background of our universe should therefore contain ghostly rings, echoes of the largest gravitational events from the previous cosmos. This is the model. This is why he searches for circles in the sky. This is why his Hawking points matter. The theory is not just an idea, it is a prediction. Most cosmologists remain unconvinced. Conformal cyclic cosmology requires assumptions about the long-term behavior of mass and matter that go beyond confirmed physics. It requires that all particles eventually become massless, which depends on physics we have not yet observed. It requires the right kind of conformal rescaling, which is mathematically clean, but physically speculative. But the model has one feature that makes it valuable, regardless of whether it turns out to be correct. It treats the question of what existed before the universe as a real, scientific, falsifiable question. It says, here is the prediction. Go look. Either the rings are there, or they are not. In the next chapter, we go look. Specifically, we look at the strangest signal Penrose claims to have found. Bright spots in the sky that, in his model, are the death cries of black holes older than our universe. In 2020, Roger Penrose and his collaborators published a paper that went further than the rings. They claim to have found, hidden in the cosmic microwave background, around 30 unusually warm patches arranged across the sky. They called them Hawking points. Each one is named after Stephen Hawking, who first showed in 1974 that black holes are not entirely black. Through a quantum process now called Hawking radiation, black holes slowly leak energy. Over time, scales vastly longer than the current age of the universe, this leakage causes them to shrink, evaporate, and eventually disappear in a final flash. For a stellar mass black hole, the evaporation timescale is around 10 to the 67 years. For a supermassive black hole of 1 billion solar masses, it is closer to 10 to the 100 years. Both numbers are so enormous that no black hole in our universe has had time to evaporate yet. Not even close. That is exactly why Penrose's claim is so radical. If we are seeing the final flashes of evaporating supermassive black holes, those black holes cannot belong to our universe. There has not been enough time. They must belong to an earlier one. In conformal cyclic cosmology, the previous aeon lasted long enough for its supermassive black holes to fully evaporate. Each evaporation produced a burst of energy. Through the conformal handshake we discussed, those bursts carry through into the next aeon and appear as concentrated warm spots in our cosmic microwave background. Hawking points. The team analyzed Planck satellite data and identified roughly 30 regions of slightly elevated temperature that, they argued, match the predicted signature. Each one would correspond to a supermassive black hole from the universe before ours, finishing its long death. The response from the cosmology community was, again, divided. Critics ran simulations to see how often such patterns would appear by chance in random noise. Several independent groups concluded that 30 warm spots of this kind are not unusual. They could appear in standard cosmology without invoking a previous universe. The Penrose team disagreed and argued the simulations did not capture the specific structure of the signal. The argument is technical. The implications are not. If Hawking points are real, they would be the first direct observational evidence of physics that existed before the Big Bang. We would be looking at the gravestones of black holes older than our cosmos. Each warm spot in the sky would mark the place where, in another universe, an entire galactic core finished its slow death. Stand with that thought for a moment. Imagine the largest object in any galaxy, a supermassive black hole holding the equivalent of billions of stars, slowly bleeding energy for a length of time so vast that the death of every star in our current universe would happen in the first blink of it. And then, finally, in a final quantum flash, vanishing. In Penrose's model, that flash made it through. We can see it. We are looking at it right now, frozen into the oldest light, scattered as warm patches across the night sky. Whether or not the model is correct, the question it forces is permanent. What does it mean for a piece of evidence to outlive a universe? What survives the transition between cosmic eras, if anything does? And what does the fact that we can even ask this question say about how far cosmology has come? Penrose's universe is not the only one that loops. There is another model of cyclic cosmology built on different math, with different assumptions, and with a different answer to the question of what came before. In this model, the universe does not flow gently from one aeon to the next. It crashes and rebounds. In Penrose's model, our universe inherits from a previous one through a smooth mathematical handshake. The previous cosmos fades into emptiness. Ours begins from that emptiness. There is another family of models that rejects the smooth handshake entirely. In these models, the universe does not end by fading. It ends by collapsing. Every galaxy, every star, every atom is pulled back together as space itself contracts. The cosmos gets smaller, denser, hotter, and faster, racing toward a single crushing point. But it never reaches that point. Just before the collapse becomes infinite, something stops it. The universe rebounds. Space starts expanding again. A new cosmos begins. This is the Big Bounce. The appeal of this idea is obvious. It removes the singularity at the center of the standard Big Bang model. A singularity is a point where the equations of physics stop working. Density goes to infinity. Temperature goes to infinity. The math collapses with the universe. Most physicists treat singularities not as real objects, but as warning signs that our theories are missing something. The Big Bounce replaces the singularity with the transition. A moment when the universe is extremely small and extremely hot, but still finite. Still describable by physics. Still part of a continuous timeline. If the Big Bounce is correct, then time did not begin with our universe. It stretches back through the contraction of the previous one. There was a yesterday before the cosmic dawn. There were stars, perhaps, or whatever the previous cosmos contained, that fell inward as their universe died. The challenge is the mechanism. What stops the collapse? What turns gravity from an inward pull into an outward push at the critical moment? Different models propose different answers. Some invoke quantum effects that become important only at extreme densities. Others invoke unknown forms of energy that resist compression. Still others invoke higher dimensional physics, where the bounce is a consequence of geometry we cannot directly perceive. The leading mathematical framework for the big bounce is called loop quantum gravity, which we will look at in the next chapter. For now, the important point is this: bouncing universe models are not science fiction. They are serious cosmological proposals, defended by serious physicists, published in peer-reviewed journals. They make different predictions than Penrose's model. They expect different patterns in the cosmic microwave background. They predict, in some versions, a slight suppression of the largest temperature fluctuations. Exactly the kind of thing that has been hinted at, though not confirmed, in Planck data. They also predict something Penrose's model does not: information transfer. In a bouncing universe, the contraction phase is causally connected to the expansion phase. Whatever happened in the previous cosmos can, in principle, leave imprints in ours, not just as ghostly rings, but as direct features in the structure of space. If true, this means the early universe is not a beginning. It is an aftermath. The smoothness we see in the cosmic microwave background is what is left over after a previous universe collapsed and rebuilt itself into ours. The slight asymmetries, the cold spots, the directional alignments may all be debris from that crash. Notice the shift this implies. We are not talking about the universe starting from nothing. We are talking about the universe starting from a different universe. The question is no longer whether something came before. The question is what kind of something and how much of it survives. To answer that, we need the math. And the strangest math on the bouncing universe comes from a theory that quantizes space itself: loop quantum gravity. And it has something specific to say about what existed on the other side of the bounce. Most physics treats space as smooth. You can divide a meter into a centimeter into a millimeter into a micrometer, and the division never stops. Space, in classical theory, is infinitely divisible. Loop quantum gravity says no. According to this theory, space is not smooth. It is grainy. At the smallest possible scale, around 10 to the minus 35 meters, space is made of tiny indivisible loops. You cannot zoom in further. There is nothing smaller. The geometry of the universe is built from these loops, the way a wall is built from bricks. This sounds abstract. It has a concrete consequence. If space is grainy, it cannot be infinitely compressed. There is a limit. Once the universe collapses to the point where all matter and energy are squeezed into the smallest possible loops, gravity cannot crush it any further. The pull inward stops. The push outward begins. In the language of the model, gravity becomes repulsive at extreme densities. Whatever was contracting now expands. The Big Crunch becomes the Big Bang. This is the loop quantum bounce, and it is the most mathematically detailed version of the bouncing universe idea. In 2006, physicist Abhay Ashtekar and his collaborators worked out the equations in detail. They found that loop quantum gravity not only allows a bounce, it predicts one. The bounce is not a special event added by hand. It comes naturally from the mathematics. What happens on the other side? According to the equations, the universe before the bounce looks similar to ours. It expands. It cools. It forms structures. Then, due to whatever forces dominate in that cosmic phase, it begins to contract. As it shrinks, density rises. As density rises, the grainy nature of space becomes important. The bounce occurs. Time on the other side runs in the same direction as time here. There is no reversal, no backwards arrow. Just a continuous flow from one expanding phase through a brief compressed transition into another expanding phase. If this picture is right, the universe has no beginning. It has only stages. The Big Bang is not an origin, it is a chapter. The model makes specific predictions. The bounce should leave subtle imprints on the cosmic microwave background, including a suppression of power at the largest scales. Some studies of Planck data have found hints of this suppression. Others have not. The signal is small, the statistics are hard, and the conclusion is genuinely undecided. There is one more consequence worth holding on to. If loop quantum gravity is correct, the universe before the bounce was not just a different universe, it was a mirror universe in a particular sense. Many of the same physical laws apply. The same matter content, perhaps. The same structures, possibly. We may be looking, when we look at the deepest features of our cosmic microwave background, at the rebuilt remains of a cosmos that was, in many ways, exactly like ours. That is a strange kind of inheritance, a cosmos built from the wreckage of a near twin. Loop quantum gravity is not the only model that proposes a beginning before the beginning. There is another one, born in string theory, that pictures the origin not as a bounce, not as a handshake, but as a collision. A collision between two vast sheets of higher dimensional space. In this model, the Big Bang did not happen at a point. It happened along a surface, and the universe was not born. It was struck. In 2001, physicists Paul Steinhardt and Neil Turok proposed something stranger than Penrose, stranger than the loop bounce, and rooted in the deepest end of theoretical physics. They called it the ekpyrotic model. The name comes from the Greek word for conflagration, a great fire. In their picture, our entire universe is a sheet, a vast three-dimensional membrane floating inside a larger space of higher dimensions. There is at least one other sheet nearby, a parallel cosmos, separated from ours by a tiny distance through a dimension we cannot perceive. For most of cosmic history, the two sheets sit close but apart. They each have their own stars, their own galaxies, their own laws. Then they meet. When the two membranes collide, the impact releases a colossal burst of energy along the entire surface. That energy is what we have been calling the Big Bang. It is not a point. It is a sheet. The hot beginning of our universe was, in this model, the moment our membrane struck another and rang like a bell. The model is built inside a framework called M-theory, which extends string theory to 11 dimensions. The math is heavy. The picture is striking. What makes the ekpyrotic model interesting is that it solves several problems in standard cosmology without invoking inflation. Inflation is the leading explanation for why the universe looks so uniform on large scales. It posits a brief period of explosive expansion in the first fraction of a second after the Big Bang. The expansion stretched tiny quantum fluctuations into the structures we see today. Inflation works, but it has open questions. It requires a specific kind of energy field that nobody has directly detected. It produces, in many versions, an endless multiverse of bubble cosmoses, which some physicists find appealing and others find deeply problematic. The ekpyrotic model offers a different mechanism. The collision between membranes naturally produces a hot, dense, almost uniform universe. The slight ripples in the cosmic microwave background come from quantum fluctuations during the slow approach of the two sheets, before the collision. No inflation field needed. The model is cyclic in a specific sense. After our universe expands and cools, the membranes slowly drift apart, then drift back together, and collide again. Each collision is a new Big Bang. Our cosmos is one in a long series of fires. If the ekpyrotic model is right, the universe has been expanding, cooling, contracting in extra dimensions, and reigniting for a length of time we cannot estimate. There may have been countless previous collisions, each one wiping the structural slate clean while preserving the underlying membranes. The predictions of this model differ from inflation in subtle but testable ways. The ekpyrotic scenario predicts a specific spectrum of gravitational waves in the early universe, that is much weaker than what inflation predicts. Future experiments designed to detect primordial gravitational waves, like the proposed Lightbird mission and ground-based observatories in Antarctica, will be able to distinguish between the two. If those experiments find strong primordial gravitational waves, inflation wins. If they find none, the ekpyrotic model and its cousins gain serious ground. Right now, the data is inconclusive. The most stringent upper limits keep tightening, but nothing has been ruled in or ruled out. So we are left with three serious models of what came before: Penrose's conformal handshake, the loop, quantum bounce, the ekpyrotic collision. Three different mechanisms, three different predictions. One question: why does any of this matter for us, sitting here on Earth, more than 13 billion years after the event? The answer comes down to one of the deepest puzzles in physics: the arrow of time. And what came before our universe is tied directly to why time moves forward at all. Drop a glass, and it shatters. The pieces never gather themselves up and leap back into your hand. Pour cream into coffee, and it swirls and mixes. The cream never separates back out and floats back into the pitcher. This is the arrow of time. It points only one way: forward. Disorder grows. Order does not assemble itself from chaos. This is one of the most reliable rules in all of physics. It is captured in the second law of thermodynamics, which says that entropy, the measure of disorder, always increases in a closed system. Here is the strange part: the basic laws of physics do not care about direction. The equations that describe the motion of atoms, electrons, and photons run perfectly well forwards or backwards in time. There is nothing in the fundamental physics that picks out a future direction. So why does the universe pick one? The answer, as far as anyone can tell, is the Big Bang. The early universe was in a state of extraordinarily low entropy, highly ordered, smooth, uniform. From that low entropy beginning, the cosmos has been increasing in disorder ever since. Galaxies form and pull matter into uneven clumps. Stars burn their fuel and scatter heat into space. Black holes grow. Information spreads. Entropy rises. The arrow of time is not a property of physics. It is a property of how the universe began. Now consider what that means. If the universe started in a low entropy state, something had to set up that low entropy. The smoothness of the cosmic microwave background, the uniform temperature, the carefully balanced energy density did not happen by accident. They were the initial conditions. And initial conditions need an explanation. Standard inflation tries to provide one. A brief period of rapid expansion smooths out any pre-existing irregularities. The result is a universe that starts ordered. But this only pushes the question back. Why was there an inflation field in the right state to drive that expansion? Why was the pre-inflationary universe set up for inflation to begin in the first place? Every model of cosmology eventually runs into this. To explain the arrow of time, you need a starting condition. To explain the starting condition, you need an earlier state. To explain the earlier state, you need something earlier still. This is exactly where pre-Big Bang models become important. They offer to push the explanation further back. In Penrose's model, the low entropy of our universe is inherited from the smoothed out final state of the previous aeon. In the loop, quantum bounce, low entropy comes from the collapse of a previous universe through the bounce. In the ekpyrotic model, it comes from the precise way two membranes approach each other before colliding. Each model has the same goal: make the arrow of time a consequence of cosmic history, not an unexplained miracle. There is one more wrinkle worth holding on to. In Penrose's model, the universe before ours had its own arrow of time, pointing forward through its own history. When that universe ended and ours began, the arrow continued. Time has been pointing the same way through both aeons. It does not reset. In the bouncing universe models, the situation is more debated. Some versions have time continuing through the bounce. Others have time effectively ending at the bounce and a new arrow starting on the other side. The honest summary is this: why time moves forward depends on what the universe looked like before there was a forward to move toward. The deeper we look at the arrow of time, the more it points us back to whatever came first. And what came first has to be something extraordinary. Because the universe began not just orderly, but impossibly orderly. So orderly that the odds of it happening by chance are smaller than any number meaningful in physics. That impossibility is the next layer, and it is where pure randomness fails as an explanation entirely. Roger Penrose once calculated the odds of our universe starting in the state it did, by chance, from random initial conditions. The number is 1 in 10 to the power of 10 to the power of 123. That is not 1 followed by 123 zeros. That is 1 followed by 10 to the 123 zeros. The number of zeros alone is far larger than the number of atoms in the observable universe. Written out, it would not fit in any volume. It would not fit in any thinkable space. That is the probability that the universe randomly started in the smooth, low entropy state we observe, functionally zero. This is the low entropy mystery, and it sits at the heart of cosmology. The early universe was extraordinarily, almost suspiciously ordered. Every direction we look in the cosmic microwave background shows a temperature uniform to 1 part in 100,000. The matter distribution was nearly perfect. The conditions were fine-tuned in exactly the way needed to produce stars, planets, and observers. The standard answer is inflation, a brief period of exponential expansion in the first sliver of a second after the Big Bang stretches any irregularities to oblivion and leaves behind a smooth, ordered cosmos. Penrose argues this is not enough. He points out that inflation itself requires a specific, low-entropy initial condition to begin. The inflation field has to be in the right state, with the right energy, in the right configuration. The probability of that configuration arising by chance is even smaller than the probability of the post-inflation universe arising directly. Inflation does not solve the entropy problem, it moves it. If the ordered start of the universe is too unlikely to be random, it has to come from somewhere. And whatever it comes from has to be itself ordered enough to produce that order. This is where pre-Big Bang models step in. In Penrose's conformal cyclic cosmology, the answer is direct. The previous universe expanded so far and emptied so completely that, by its end, it had become smooth on the largest possible scale. That smoothness was the conformal handshake. It became the smooth start of our universe. The order is not generated, it is inherited. In the bouncing universe models, the answer is similar in spirit. The previous cosmos, during its contraction, smoothed itself out under specific conditions. The bounce passed that smoothness through. Our universe inherited an ordered seed. In the ekpyrotic model, the smoothness comes from the careful approach of the two membranes, before collision. The slow drift across higher dimensional space allows quantum fluctuations to settle into a near uniform state. The collision then ignites that state into our hot beginning. Each model offers a different answer to the same question. None of them invent order. They explain where the order came from. And here is the unsettling implication. If the order of our universe came from somewhere, then our universe is not the original. There was an earlier system. That earlier system was itself ordered, which means its order also came from somewhere. The chain extends backward. Some cosmologists are comfortable with this. They argue the chain goes back forever. Others argue the chain must end somewhere, in a state of pure timelessness or quantum potential that does not require explanation. Either way, the low entropy mystery is a powerful argument that something existed before our universe. A random beginning is too improbable to take seriously. An inherited beginning requires a parent. The math points to a parent. The cosmic microwave background may carry traces of one. The bounce, the handshake, The collision are three different ways to describe the inheritance. But the inheritance might not be the only thing carrying through. Because something else is happening in the deep sky, something that has nothing to do with theory and everything to do with telescopes. The James Webb Space Telescope is finding galaxies that should not exist. Not in the wrong place, not the wrong size, in the wrong era. The James Webb Space Telescope launched on Christmas Day in 2021. It is the most powerful space telescope ever built. Its mirror is 6.5 meters across. Its instruments see in the infrared, which means it can detect light that has been stretched by the expansion of the universe over billions of years. The longer the journey, the more the light stretches. The deeper into the past Webb can see. When Webb began returning data in 2022, astronomers expected to see the first faint, scrappy galaxies forming in the early universe. Small, irregular, dim. The kinds of things you would expect from cosmic infants only a few 100 million years old. That is not what Webb found. In its first images of the deep past, Webb returned pictures of galaxies that were too big, too bright, and too organized to exist when they did. Some of them appeared to be fully formed disk galaxies, complete with a rotational structure, massing hundreds of billions of solar masses, only 500 million years after the Big Bang. According to standard cosmology, that should not be possible. The problem is time. Galaxies form by gravity slowly pulling matter together over hundreds of millions of years. Stars need time to ignite. Black holes need time to grow. Disks need time to settle into rotation. The standard timeline says galaxies of the size and complexity Webb is seeing should take several billion years to assemble. Webb is seeing them at a fraction of that age. There are several possible explanations. The first is that the redshift measurements are wrong. Astronomers determine how old a galaxy is partly by how stretched its light is. In the early data, some redshifts were estimated from photometry, which is less precise than spectroscopy. As more spectroscopic measurements came in, some of the most extreme cases were revised. Some of the impossibly old galaxies turned out to be merely very old, but not all of them. Even after careful spectroscopic confirmation, Webb has identified galaxies whose mass and structure remain difficult to reconcile with standard models. The discrepancy is real, even if it is smaller than the first headline suggested. The second possibility is that galaxies form faster than we thought. Maybe star formation in the early universe was more efficient than current models predict. Maybe gas collapsed into stars more rapidly. Maybe the first generation of stars was much more massive and burned through their fuel faster, seeding the next generation of galaxies in record time. This would require revising several models of galaxy formation, but it would not break cosmology. It would refine it. The third possibility is more uncomfortable. Maybe the universe is older than we think. If the cosmos is, say, several billion years older than the standard estimate of 13.8 billion, then the Webb galaxies have had more time to form. The age problem disappears, but a new problem appears. The standard model of cosmology fits the cosmic microwave background, the Hubble expansion rate, and the abundance of light elements remarkably well. Changing the age of the universe means changing all of those calibrations. Some theorists are willing to do exactly that, as we will see in 2 chapters. The fourth possibility, the strangest one, is that the early universe contained structures we are not modeling. Primordial black holes, for example, could have seeded galaxy growth long before normal star formation was possible. If huge black holes existed shortly after the Big Bang, they would pull in matter rapidly and produce massive galaxies on a timeline Webb is now revealing. We will return to those black holes in Chapter 18. For now, hold on to one fact. Our most powerful telescope, looking at the deepest accessible past, is finding things that contradict our best models. The contradictions are real, even after careful checking. The early universe was busier, faster, and more structured than any standard prediction allowed for. And the strangest part is what comes next. Some of the light Webb is collecting may not just be from the early universe. It may be from a universe that, by some interpretations, is older than the universe is supposed to be. Light from distant galaxies arrives stretched. The longer it travels, the more it stretches. The amount of stretching is called redshift, and it tells us how far away the galaxy is and how long ago its light was emitted. A high redshift means a long journey. A long journey means a young universe at the time of emission. For decades, the highest measured redshifts came from quasars and distant galaxies at redshift 7, 8, 9. These objects were seen as they existed about 1 billion years after the Big Bang. Already very early. Already very strange. Then Webb began pushing the limit. In 2023, astronomers reported a galaxy named JADES-GS-Z14-0 with a confirmed spectroscopic redshift of about 14. Light from this galaxy left it when the universe was only about 290 million years old. That is the most distant galaxy ever confirmed. It is not just distant. It is bright. Brighter than expected. Bigger than expected. More mature than expected. When Webb measures other galaxies at redshifts of 13, 12, and 11, the same pattern repeats. Many of them appear too developed for their epoch. They have already produced multiple generations of stars. Their chemistry contains heavier elements that should require more time to forge. Then, there is the more provocative claim. In 2023, astronomer Rajendra Gupta proposed that the universe might be 26.7 billion years old, nearly twice the standard estimate. His argument focused on a specific way light might lose energy over cosmic distances, an effect called tired light, combined with a modified cosmological model. His paper drew immediate criticism. Most cosmologists reject the tired light component because it has been ruled out by multiple independent observations, including the precise blackbody spectrum of the cosmic microwave background. A genuinely tired light universe would not produce the kind of cosmic background we observe. But the underlying tension Gupta was responding to is real. Webb is finding galaxies that look chemically and structurally older than they should be. Some of those galaxies, when their stellar populations are analyzed, contain stars that appear to be more than 1 billion years old, at a time when the universe itself was supposed to be less than 1 billion years old. This is not a small discrepancy. A galaxy cannot contain stars older than the universe. The standard answer is that the stellar age estimates are uncertain. Stars in distant galaxies are dated by their light, and light from young, massive stars can sometimes mimic the signature of older populations. Careful reanalysis usually shrinks the apparent age, usually, but not always. Some of the Webb measurements still produce age estimates that, taken at face value, push against the cosmic timeline. The community is divided on how to handle these. Some argue the methods are flawed, others argue we should trust the data and revise our models. The most cautious framing is this: our best telescope is showing us things that, if confirmed, may require us to revise either how galaxies form, how stars age, or how old the universe is. None of those revisions are small. All of them are being seriously discussed in the published literature. There is one more piece to this puzzle, and it predates Webb by years. It is a measurement crisis that has been quietly growing in cosmology for over a decade, one that suggests our basic equations for the expansion of the universe may be incomplete. Two reliable methods of measuring how fast the universe is expanding give two different answers. The gap between them keeps getting wider. It is called the Hubble tension, and it may be hinting at physics we have not yet discovered. Possibly physics from before the Big Bang. The universe is expanding. Galaxies are moving apart from one another. The rate of that expansion is described by a single number called the Hubble constant. It tells us how fast space stretches per unit of distance. For most of the last century, measuring the Hubble constant was a noisy business. Different methods gave different answers. The disagreements were attributed to imprecise instruments and unknown systematic errors. Then, the instruments got better. There are two main ways to measure the Hubble constant. The first is to look at the cosmic microwave background. By analyzing the patterns in the oldest light and feeding them through the standard model of cosmology, you can calculate how fast the universe must be expanding today. The Planck mission did this in 2018 and got a value of about 67.4 kilometers per second per megaparsec. The second method is to measure distances to nearby galaxies directly, using stars whose intrinsic brightness is known. By comparing the brightness we see to the brightness we expect, we can calculate distance. By measuring how fast those galaxies are moving away, we can calculate the expansion rate. A team led by Adam Rees, who won the Nobel Prize for discovering dark energy, has spent years refining this method. Their value, as of recent measurements, is around 73 kilometers per second per megaparsec. The two numbers do not agree. The gap is about 8%. That sounds small. In cosmology, it is not. Both measurements have shrinking uncertainties. The disagreement is more than 5 sigma, which is the standard threshold for a confirmed scientific result. In other words, the disagreement is real. Both methods are giving real answers. They just disagree about what the universe is doing. This is the Hubble tension, and it has not gone away. As measurements have improved, the tension has grown stronger, not weaker. There are 3 broad categories of explanation. The first is hidden systematic errors. Maybe one of the methods has a flaw nobody has found yet. Maybe the calibration of the distance ladder is off in some subtle way. Maybe the Planck analysis is missing something about how the cosmic microwave background formed. Many cosmologists have spent years hunting for such errors. None have been found that come close to closing the gap. The second is new physics in the late universe. Maybe dark energy. The mysterious force pushing galaxies apart behaves differently than we think. Maybe its strength changes over time. Maybe there is a new component of the cosmos, sometimes called early dark energy, that briefly tweaked the expansion rate around the time of the cosmic microwave background. The third is new physics from before the universe began. Some theorists argue the Hubble tension is a fingerprint of pre-Big Bang structure. If our universe inherited specific initial conditions from a previous state, those conditions might affect the expansion rate in ways the standard model does not capture. The discrepancy between the two measurement methods would reflect a real difference between what the early universe was doing and what our equations assume it was doing. This is speculative. It is also serious. Physicists at major institutions have published peer-reviewed papers exploring exactly this possibility. What is no longer speculative is this. 2 of the most carefully calibrated measurements in cosmology give different answers about the basic expansion rate of the universe. Something is missing from our model. The standard story of the Big Bang as a clean, explained beginning has cracks in it. Those cracks are widening. When you put the JWST galaxies, the redshift surprise, and the Hubble tension together, a pattern emerges. The universe seems to be older, busier, and more complex than our standard model allows. Some cosmologists are starting to take a once fringe possibility seriously. The universe, the actual full universe, may be much older than 13.8 billion years. The age of the universe, 13.8 billion years, is one of the most quoted numbers in modern science. It comes from a careful combination of multiple measurements, including the cosmic microwave background, the abundance of light elements, and the ages of the oldest known stars. The number is consistent, it is precise, and it is increasingly under pressure. The pressure comes from 3 directions at once. First, the JWST galaxies. Some of them appear too mature for the standard timeline. If they are as old as their chemistry and structure suggest, the universe needs more time than 13.8 billion years to have produced them. Second, the Hubble tension. The disagreement between local and cosmic measurements of expansion may indicate the cosmos has been evolving for longer than the standard model assumes. Third, certain stars in our own galactic neighborhood. There is a star called HD140283, sometimes nicknamed the Methuselah star, whose age has been estimated at 14.5 billion years, with an uncertainty of around 800 million years. That uncertainty range overlaps with the standard age of the universe, but the central value is older than the universe itself. Most astronomers attribute this to measurement uncertainties. Some take it as another small signal that something is off. These three lines of evidence have not forced a paradigm shift. They have, however, opened the door to fringe and semi-fringe proposals that the standard age estimate is wrong. The most radical proposal came from astrophysicist Rajendra Gupta in 2023. He argued that by combining a modified expansion model with a hypothesis about how light loses energy over cosmic distances, the universe could be 26.7 billion years old, nearly twice the standard estimate. The proposal received attention, but not consensus. Most cosmologists pointed out that the tired light component of his model is incompatible with the precise blackbody shape of the cosmic microwave background, which has been measured exquisitely well. A universe with significant tired light would not have a perfect blackbody background. Ours does. So Gupta's specific model is widely considered wrong, but the question he raised remains. Even without tired light, can the universe be older than 13.8 billion years? Some serious models say yes, by smaller margins. If the parameters of the standard model are tweaked, particularly the behavior of dark energy in the early universe, the age can shift by 1 billion years or more. None of these tweaks are mainstream consensus. All of them are being explored. What does this mean for the question of what came before? If the universe is older than we think, the early period was longer. Galaxies had more time to form. Stars had more time to age. The mysterious anomalies in the cosmic microwave background had more time to develop or to be inherited from previous structure. A longer cosmic history makes some pre-Big Bang models more comfortable and others more uncomfortable. Penrose's conformal cyclic cosmology, for example, does not strongly depend on the age of the current aeon. The handshake works regardless. The bouncing universe models also accommodate variable ages, though some predictions shift. There is one consequence worth holding on to. If the standard age of the universe is wrong by even 1 billion years, then the most fundamental measurement in cosmology has a systematic error nobody has yet found. That kind of error would not just be a technical inconvenience, it would be a sign that our basic picture of cosmic origin is incomplete. Incompleteness is the recurring theme, the cold spot, the axis of evil, the hemisphere problem, the Hawking points, the JWST galaxies, the Hubble tension, the age question. None of these on its own breaks cosmology. Together they suggest the standard story of a clean Big Bang followed by smooth expansion is not the full story. There is more underneath. And one of the strongest hints of that underneath is something we have not yet talked about. Objects that may have formed before stars existed. Possibly before our universe existed at all. Black holes that did not come from collapsing stars. Black holes that came from something earlier. Every black hole you have read about in news headlines came from a dying star. A massive star runs out of fuel, its core collapses, and gravity wins. The result is a black hole, born from the death of something that lived. There is another kind. They have never been confirmed. They are also nearly impossible to rule out. Primordial black holes are objects that, if they exist, formed in the first fraction of a second after the Big Bang, maybe even earlier. They were not created by stellar collapse. They were created directly, when patches of the early universe were so dense that they collapsed under their own gravity before anything we would recognize as matter had even formed. Stephen Hawking proposed them in 1971. The idea has come and gone from fashion many times since. What makes them interesting now is that they could solve several problems at once. The first problem is dark matter. The universe contains roughly 5 times more invisible mass than visible mass. We see its effects on galaxies and on the cosmic microwave background, but we cannot see the substance itself. For decades, the leading candidate was a new kind of subatomic particle. Despite enormous experimental effort, no such particle has been detected. Some cosmologists are turning back to primordial black holes as an alternative. If a population of small black holes formed in the early universe and never decayed, they could be the dark matter. They would interact with normal matter only through gravity, exactly as dark matter does. The second problem is the JWST galaxies we discussed in Chapter 14. If primordial black holes existed in the very early universe, they would have acted as seeds for galaxy formation. Matter would fall into them. Stars would form around them. Galaxies could grow much faster than the standard model predicts. The mystery of mature galaxies appearing too early would have an answer. The third problem is the most strange. Some theorists argue that primordial black holes might not have formed inside our universe at all. They might have formed in the previous one. If a bouncing universe model is correct, black holes that were small enough to survive a bounce could carry through into the current cosmos. We would inherit them. This is speculative. The math is debated. But the implication is striking. Some of the dark matter holding our galaxies together might be made of objects that predate the Big Bang. The observational evidence so far is mixed. Gravitational wave detectors, particularly LIGO, have spotted black hole mergers that some teams interpret as primordial in origin. Other teams attribute the same signals to ordinary stellar black holes. The signatures are similar enough that the two cannot yet be distinguished cleanly. Microlensing surveys, which look for black holes by the way their gravity bends light from background stars, have placed limits on how many primordial black holes can exist in certain mass ranges. These limits rule out some scenarios but leave others wide open. There is a window, between about 10 times the mass of our home star and a few hundred solar masses, where primordial black holes could account for a significant fraction of dark matter and remain undetected. Future observations from gravitational wave detectors and from missions like Euclid and the Roman Space Telescope will narrow the possibilities further. Whether or not primordial black holes turn out to be real, they represent a category of object that by definition came before everything else. If even one is confirmed, the universe gains a kind of inheritance. There would be ancient relics inside us, holding together the galaxies that hold together the planets that hold together the lives we are living right now. The next inheritance is even more invisible, and it accounts for most of the matter in the cosmos. 5 out of every 6 grams of matter in the universe is invisible. You cannot see it. You cannot touch it. You cannot detect it with any telescope at any wavelength. It does not interact with light. It does not interact with normal matter through any force we have measured, except gravity, but it is there. Galaxies rotate too fast for the visible matter alone to hold them together. Galaxy clusters move in ways that demand more mass than we can see. Light from distant objects bends around invisible mass concentrations. The cosmic microwave background carries the imprint of this hidden substance in its tiniest fluctuations. Whatever it is, dark matter outweighs everything you have ever observed by a factor of 5 to 1. For decades, particle physicists assumed dark matter was a new kind of particle. The leading candidate was called the WIMP, short for weakly interacting massive particle. Underground detectors were built. Vast amounts of money were spent. Year after year, the experiments came up empty. Other candidates had been proposed and tested. Axions, sterile neutrinos, primordial black holes, modified gravity. None has been confirmed. Some have been seriously constrained. The honest summary is that we know dark matter exists, and we do not know what it is. This is where the question of what came before becomes interesting. If dark matter is not a particle of the standard model, where did it come from? The answer might be that it came from a different epoch entirely. Some cosmologists propose that dark matter is a relic from before inflation. a leftover from whatever physics governed the universe in its earliest moments, before the rapid expansion smoothed everything out. If that is true, dark matter is not just old. It is older than the cosmic microwave background, older than the first atoms, older than the moment when light could travel freely. It would predate visibility itself. In some bouncing universe models, this idea goes further. If our universe inherited matter from a previous cosmos, the most stable forms of that matter would survive the bounce. Particles that did not interact strongly with the rest of physics would pass through unchanged. They would arrive in our universe as a quiet, gravitating presence that shapes structure but never reveals its origin. Dark matter in this picture is not a new kind of stuff. It is old stuff, survivor matter, whatever was robust enough to live through the transition. There is one specific piece of evidence that fits this picture uncomfortably well. The distribution of dark matter in galaxies tends to be smoother than the distribution of visible matter. It clumps less. It settles into broader, gentler shapes. This is sometimes interpreted as evidence that dark matter has been around longer than visible matter and has had more time to relax into its current form. The more conservative explanation is that dark matter is simply collisionless. It does not lose energy through interactions, so it does not collapse into tight structures the way gas does. Both explanations are consistent with the data. The pre-Big Bang version is harder to test, but harder to rule out. What we can say with confidence is this: the dominant form of matter in the universe is unknown. It does not fit any particle we have detected. Its origin is unexplained by the standard model of physics, and the simplest explanations have failed for 40 years. Something gravitating is everywhere we look. We do not know what it is. We do not know when it formed, and we cannot rule out that it formed before the universe officially began. There is another mystery from the early cosmos that pulls in the same direction. A mismatch between what physics predicts the early universe should have produced and what it actually did produce. The chemistry does not add up. Specifically, an element you find in batteries is missing. In the first 3 minutes after the Big Bang, the universe was a hot, dense plasma. Protons and neutrons collided, fused, and built the first atomic nuclei. This process is called Big Bang nucleosynthesis. It produced the lightest elements: hydrogen, helium, and tiny amounts of lithium and beryllium. The amounts can be calculated. The standard model of physics, applied to the conditions of the early universe, gives precise predictions for how much of each element should have been created. For hydrogen and helium, the predictions match observations almost perfectly. The agreement is one of the great triumphs of modern cosmology. For lithium, it does not match. Specifically, the isotope known as lithium-7. The standard model predicts a certain abundance. When astronomers measure the actual amount in old stars, they find roughly 3 times less than predicted. The discrepancy has been confirmed by multiple independent measurements over decades. It is not going away. This is the lithium problem. The mismatch is not enormous in absolute terms. We are talking about a small fraction of all atoms, but it is large in statistical terms. The prediction and the measurement disagree by a factor of 3 to 4, with very small error bars on both sides. Several explanations have been proposed. The first is that the measurements are wrong. Maybe stars destroy some of their lithium over time, so what we see today is less than what was originally there. This is plausible, but careful studies of lithium in different stellar environments suggest the destruction process cannot fully account for the gap. The second is that the predictions are wrong. Maybe the standard nuclear physics used to calculate Big Bang nucleosynthesis has a small error. Researchers have hunted for such errors for years. Nothing has been found. The third is more interesting. Maybe the early universe contained physics we have not modeled. New particles, new interactions, or new fields could alter how lithium was produced or destroyed in the first minutes. Some theorists have proposed that decaying particles from before the standard era of nucleosynthesis could have eaten into the lithium budget. Particles from before. That phrase keeps appearing. If a population of unstable particles existed in the very early universe and decayed during nucleosynthesis, they could have produced energetic photons that broke apart lithium nuclei. The result would be less lithium than the standard model predicts. The measurement would match. What are these particles? Where did they come from? The honest answer is that nobody knows. They would not be part of the standard model of particle physics. They would be relics from an even earlier era, possibly from the inflation phase, possibly from before. Some theorists tie this directly to pre-Big Bang scenarios. In bouncing universe models, particles from the previous cosmos that survived the bounce might have decayed during our universe's nucleosynthesis. Their decay products would interfere with lithium formation in exactly the way needed to explain the discrepancy. This is speculative. It is also one of the few clean ways to explain the lithium problem without inventing arbitrary new physics. The lithium problem is small in scale and large in implication. It is a quiet signal from the first 3 minutes that something extra was in the early universe. Something not accounted for in the standard model. Something that left a fingerprint on the chemistry of the cosmos. That fingerprint is on every old star ever measured. We cannot remove it. We can only explain it. And the cleanest explanations point to particles that should not exist in our model of physics. The lithium problem may not be the only such fingerprint. There are others. Some involve particles that physicists have spent decades searching for, sometimes finding hints, sometimes not. One of those particles, if it exists, would carry information from before the standard model itself was relevant. It is called the sterile neutrino, and it keeps almost showing up. Neutrinos are the strangest particles we know about for sure. They are produced by the trillions in the core of stars, in nuclear reactors, and in cosmic ray showers. They pass through ordinary matter as if it were not there. Right now, about 100 trillion neutrinos from our home star are passing through your body every second. They will not stop. They will not interact. They will continue out the other side of Earth and onward into space. 3 types of neutrinos are known. They are called electron, muon, and tau. They are part of the standard model. They have been detected, measured, and studied for decades. A 4th type has been theorized for almost as long. It is called the sterile neutrino. The name comes from the fact that, unlike the 3 known types, it would not interact with the weak nuclear force. It would interact only through gravity. It would be even harder to detect than the others. If sterile neutrinos exist, they would carry information that the rest of the standard model does not contain. They would also be a candidate for dark matter, particularly in a mass range that conventional WIMP searches cannot reach. For 30 years, experiments have been hunting for them. The history is messy. In the 1990s, an experiment called LSND at Los Alamos National Laboratory found anomalies in neutrino oscillation data that could be explained by sterile neutrinos. The result was inconclusive but suggestive. A follow-up experiment called Minibuni, designed to test the LSND result, found similar anomalies. Other experiments, like IceCube at the South Pole, found no evidence of sterile neutrinos in the regions where they were expected. The picture remains unresolved. Some experiments hint at sterile neutrinos. Others rule them out, in some mass ranges. A definitive detection has not happened. A definitive ruling out has not happened either. In 2022, the Microboon experiment at Fermilab released results that disfavored the simplest sterile neutrino interpretation of the earlier anomalies. The results did not rule out all versions of sterile neutrinos, but they removed the most straightforward explanation for several long-standing puzzles. The story is not over. Future experiments at Fermilab and elsewhere will probe different mass ranges and different interaction patterns. The hunt continues. What makes sterile neutrinos relevant to the question of what came before is the kind of physics they would represent. They are not predicted by the standard model. They would require extending it. The way they might extend it has implications for cosmology. In some theoretical frameworks, sterile neutrinos are connected to the matter-antimatter asymmetry of the universe. Our cosmos contains far more matter than antimatter. The standard model cannot explain why. If sterile neutrinos exist with the right properties, their decays in the very early universe could have tilted the balance, leaving behind the matter we see today. This means sterile neutrinos, if real, would be witnesses to physics from before the cosmic microwave background. They would carry information about a phase of the universe we cannot observe directly. Some theorists go further. They argue that sterile neutrinos, if they have the right mass and properties, could be the primary form of dark matter. They could have been produced before inflation and survived as a quiet, invisible substance ever since. They would be relics of the deep past. The honest summary is that sterile neutrinos are a maybe. The evidence is suggestive but not conclusive. The theoretical motivation is strong. The experimental hunt has been long and inconclusive. What the sterile neutrino debate illustrates is something larger. The standard model of particle physics is incomplete. Several lines of evidence, including neutrino oscillations, the matter-antimatter asymmetry, the lithium problem, and dark matter, all point to physics beyond what we currently understand. Some of that physics is from earlier than we can probe directly. Some of it might be from before the universe began. The cosmic microwave background carries another fingerprint of that incompleteness. Not just a cold spot. A long, strange band of cold sky stretching across the heavens. In 2021, a team of astronomers reanalyzing Planck data identified a curious feature that had not received much attention before. Not a single cold spot. A long, narrow region of slightly lower temperature stretching across a wide arc of the sky. A cold streak. It is more subtle than the original cold spot. It does not show up dramatically in single pixel temperature maps. It emerges when researchers apply specific kinds of statistical filters that emphasize elongated structures. The streak runs across a substantial fraction of the visible cosmic microwave background. It is not perfectly straight. It curves slightly. It is colder than its surroundings by a small but statistically significant amount. This kind of feature is harder to explain than a single cold spot. A single spot can be attributed to a supervoid, or a cosmic texture, or a statistical accident. A long arcuate cold region requires either a much larger underlying structure or a more exotic mechanism. Several explanations have been considered. The first is foreground contamination. Maybe the streak is caused by emission from our own galaxy or from intervening dust that has not been fully subtracted. This is the boring explanation, and it is the one most cosmologists initially favored. Detailed analysis has not been able to fully eliminate the streak through foreground subtraction, but it has not been able to confirm it as a true cosmological signal either. The second is gravitational lensing. The light of the cosmic microwave background has traveled through billions of years of cosmic structure. Galaxy clusters and large-scale matter distributions deflect that light slightly. A long, elongated arrangement of structures along a particular line of sight could create a cold streak through subtle lensing effects. The third is the most interesting. The streak might be a signature of a primordial defect. In the early universe, as matter cooled from one phase to another, the symmetries of the underlying physics could have broken in different ways in different regions. Where two regions met, a defect could have formed. Defects come in different shapes. Point-like defects are called monopoles. Line-like defects are called cosmic strings. Sheet-like defects are called domain walls. Cosmic strings, in particular, have been a theoretical interest for decades. They would be incredibly thin, incredibly long, incredibly massive lines of energy stretching through space. A single cosmic string could span the observable universe. Its gravity would be enormous along its length. Its passage would imprint a thin, cold streak on the cosmic microwave background. Cosmic strings have been searched for extensively. Several types have been ruled out. Others remain possible. particularly at lower energy scales than the original models predicted. If the cold streak observed in 2021 is a cosmic string signature, it would be the first direct evidence for one. It would also tell us something specific about the early universe. It would mean a phase transition occurred that left a one-dimensional defect behind. The transition would have happened at energies far higher than anything we can produce in laboratories. Some theorists go further and propose that cosmic strings could have formed before our universe began. In bouncing or cyclic models, defects from a previous cosmos could survive into the current one. The cold streak would then be a survivor from before. This is speculative. The streak itself has not been confirmed as a real signal by independent analyses with the same level of confidence as the original cold spot. The community treats it as suggestive but uncertain. What it adds to our growing pile is one more directional anomaly in the oldest light. A faint, long cold mark across the sky. With no clean explanation in the standard model, the pile is no longer small. The cold spot, the axis of evil, the hemisphere problem, the Hawking points, the cold streak, each one alone is dismissible. Together they form a pattern, and the pattern grows when we stop looking at the cosmic microwave background and start looking at galaxies. Because the largest known structures in the universe should not exist either. Modern cosmology rests on a simple assumption called the cosmological principle. It states that on large enough scales, the universe is homogeneous and isotropic, same density everywhere. No preferred direction, no special places. The principle is a working assumption, not a law of nature. If it breaks, the standard model of cosmology breaks with it. It is starting to break. In 2021, a graduate student at Central Lancashire University in England named Alexia Lopez was analysing data from the Sloan Digital Sky Survey. She was looking at the absorption signatures of magnesium in the spectra of distant quasars. Each absorption signature marks a galaxy along the line of sight. Mapping enough of them, you can trace the distribution of matter across vast volumes of space. Lopez found something that should not be there. A nearly perfect arc of galaxies, 3.3 billion light-years across, stretching across 1/15 of the entire observable universe. She named it the Giant Arc. The cosmological principle says structures of this size should not exist. According to standard models, the largest possible coherent structures in the universe should be around 1.2 billion light-years across. The Giant Arc is nearly 3 times that limit. The probability of such a structure forming by chance from the standard model is very small. Lopez estimated it at less than 1 in 1,000. The discovery was not isolated. In 2024, Lopez's team announced a second structure, even larger. They called it the Big Ring, roughly 1.3 billion light-years across, with a near-perfect circular geometry. It sits in the same general region of sky as the Giant Arc, at a similar distance from us. 2 enormous structures in the same direction, both violating the size limit set by standard cosmology. The community response has been cautious. Some researchers have argued that the patterns are real, but might be visual coincidences, where the apparent ring or arc structure is partly an artifact of the viewing angle. Lopez and her colleagues have pushed back, arguing that the statistical significance is too high to dismiss as coincidence. The honest summary is that 2 extraordinary large structures have been identified that the cosmological principle does not allow. The structures are real. The interpretation is debated. If the structures are confirmed, and if no statistical fluke explains them, the implications are serious. The cosmological principle would need to be modified. The largest scales of the universe would not be smooth. They would carry structure that exceeds the size of our standard models. Where would such structure come from? The answer, in any modified model, has to involve physics that operates on scales larger than the standard inflationary expansion can produce. That points either to non-standard inflation, to defects from the early universe, or to inheritance from a previous cosmos. The same theme keeps returning. When the universe shows us things our standard model cannot accommodate, the candidate explanations either require new physics within our universe, or invoke conditions established before our universe. The giant arc and the Big Ring are not the only oversized structures. There are others, including some that have been known for years, and are even larger. The Sloan Great Wall, identified in 2003, stretches roughly 1.4 billion light-years. The Hercules Corona Borealis Great Wall, identified in 2013, may extend more than 10 billion light-years across the universe, although its existence as a single coherent structure is debated. Each of these structures, if real, exceeds the size limits of standard cosmology. Each one challenges the assumption that the universe looks the same in every direction at large enough scales. Each one suggests either that the standard model is missing something, or that the universe contains imprints from a phase we have not yet understood. Which leads us to ask, how big can a structure be before it stops being just a structure and starts being a feature of cosmic origin? The Hercules Corona Borealis Great Wall is the largest known structure in the universe. If you accept that it is a single coherent structure, that is a real if. The wall was identified in 2013 by a team led by astronomer Istvan Horvath, using data from gamma-ray bursts. Gamma-ray bursts are the brightest explosions in the universe, often associated with the deaths of massive stars or the mergers of neutron stars. They can be seen across vast distances. By mapping where they occur, astronomers can trace where galaxies are clustered, since most bursts happen in regions of active star formation. Horvath's team noticed an unusual concentration of bursts in a specific region of sky and a specific range of distances. The concentration was so dense that they argued it had to correspond to a real structure of galaxies. They mapped its extent and found it stretched across a region roughly 10 billion light-years long. 10 billion light-years is more than 7 times the size of any structure the cosmological principle allows. If the wall is real and coherent, it represents a violation so extreme that it would force a fundamental rethinking of large-scale cosmology. The community response has been split. Some teams have supported the original analysis and argued that the gamma-ray burst concentration is statistically significant and cannot be a fluke. Others have pushed back, arguing that gamma-ray burst surveys have selection effects that can create the appearance of structure where there is none. The wall might be partly real, and partly an illusion of how the data is collected. The debate has not been settled. The Hercules Corona Borealis Great Wall remains a maybe. A controversial maybe. Better established is the Sloan Great Wall. Identified in 2003 from the Sloan Digital Sky Survey, it is a clear concentration of galaxies stretching about 1.4 billion light-years across the sky. That is still larger than the cosmological principle allows, by about 20%. The Sloan Great Wall is not in dispute. It is real. The concentration of galaxies along its length is well established. Its size is the issue. For 2 decades, cosmologists have debated whether the Sloan Great Wall represents a genuine structural anomaly or whether it sits on the border of what standard models can produce. Some statistical analyses suggest it is just barely consistent with the standard picture. Others suggest it is mildly inconsistent. What is not debated is that we keep finding structures at the edges of what our models allow. Add the Sloan Great Wall, the Hercules Corona Borealis Great Wall, the giant arc, the Big Ring, and the original cold spot together. Each one is at or beyond the limits of standard cosmology. The chance that all of them are statistical accidents in the same direction of mild violation is small. A pattern of small anomalies is sometimes more telling than a single large one. The pattern suggests that the universe has structure at scales larger than the standard model can explain. The structures are not absurdly large in absolute terms. They are the kind of large that suggests our equations are missing a small but important factor in how cosmic structure formed or was inherited. The sources of that missing factor, if it exists, are limited. New physics within our universe, or input from before our universe. Either way, the largest structures we can map are quietly insisting that the smooth, simple, standard cosmos is not the full picture. There is one more structural anomaly worth introducing. It is not about the size of objects. It is about the direction they are moving. Large numbers of galaxy clusters appear to be flowing through the universe in a coherent direction, a direction that points toward something outside the observable cosmos. In 2008, astronomer Alexander Kashlinsky at NASA Goddard Space Flight Center reported a result that sounded impossible. Galaxy clusters across vast regions of the observable universe seem to be moving together, not falling toward nearby gravitational sources, not drifting randomly, flowing as a group in a specific direction at speeds of several hundred kilometers per second. He called it the dark flow. The direction of the flow was unusual. It pointed toward a region of sky between the constellations Centaurus and Vela. Crucially, it did not point toward any visible structure that could be pulling the clusters that way. The standard explanation for galaxy cluster motion involves gravitational attraction from nearby concentrations of mass. The dark flow had no such source. The clusters appeared to be moving towards something that was not in our observable universe. The original analysis used a technique that measures small temperature shifts in the cosmic microwave background caused by hot gas in moving galaxy clusters. The technique is called the kinematic Sunyaev-Zeldovich effect. Kashlinsky and his colleagues argued that the temperature shifts they detected indicated bulk motion of hundreds of clusters in a coherent direction. The result was controversial from the start. Other teams reanalyzed the data using slightly different methods and reached different conclusions. Some confirmed a flow, but at lower velocities. Others found no significant flow at all. The Planck satellite team performed their own analysis in 2014 and reported that they could not confirm the dark flow at the original strength. The debate is unresolved. The dark flow is either a real cosmic mystery or a statistical artifact in a specific kind of analysis. Independent verification remains difficult because the signal is small and the technique is sensitive to systematic errors. If the dark flow is real, the implications are dramatic. A coherent flow of galaxy clusters towards something outside our observable universe would suggest that the observable universe has a neighbor. Something massive enough to influence the motion of distant structures, but far enough away that its light has not yet reached us. In standard inflationary cosmology, this is hard to arrange. The observable universe is supposed to be representative of the larger cosmos. There should not be massive concentrations of matter just outside our horizon, pulling on clusters inside it. In some non-standard models, it is possible. If our universe is one of many bubble cosmoses formed during eternal inflation, then nearby bubbles could exert subtle influence on ours during the earliest moments. The dark flow could be a memory of that influence. A tilt in the cosmos imprinted before our universe became smooth. In bouncing universe models, the dark flow could be even older. It could be inherited motion from the previous cosmos, transferred through the bounce. The galaxy clusters of today would be flowing in a direction set by structures that no longer exist. These interpretations are speculative. The dark flow itself is contested, but the pattern is consistent with what we have seen elsewhere in this story. Anomalies that, taken individually, can be dismissed. Anomalies that, taken together, point toward physics or history beyond our standard picture. What the dark flow forces us to consider is the possibility that the observable universe is not isolated. We may be embedded in a larger structure. We may be moving through it. We may carry, in the quiet drift of clusters across billions of light years, the imprint of something larger than the cosmos we can see. The natural next question is whether this is just one universe among many, whether the larger structure is itself made of universes, and whether some of those universes may be older than ours. This is the territory of bubble universes and eternal inflation, and the mathematics of it is unsettling. The standard model of cosmic origin includes a phase called inflation. In the first tiny fraction of a second after the Big Bang, space expanded by a factor of more than 10 to the 26th. The universe doubled in size many dozens of times in less time than it takes a particle of light to cross an atom. Inflation explains several things: the smoothness of the cosmic microwave background, the flatness of space, the lack of certain exotic particles that simpler models would predict. It also has a consequence that many physicists find uncomfortable. In most versions of the theory, inflation does not stop everywhere at once. Inflation is driven by a kind of energy field. Where the field is in the right state, expansion is exponential. Where it transitions to a different state, expansion slows and a region of space settles into something like our universe. The settled region is a bubble. Inflation continues outside the bubble in the surrounding inflating space forever. This is called eternal inflation. The key feature is that the inflating space outside any bubble keeps growing, faster than bubbles can ever swallow it. Even though new bubbles keep forming, the inflating background expands so quickly that the total volume of inflating space always outpaces the total volume of settled bubbles. The result is an infinite, eternal multiverse. Bubbles are forming all the time. Each one is its own universe. Each one has its own physical laws, its own starting conditions, its own history. Some are older than others. Some may have ended. Some may still be expanding. Some may contain observers. Our universe in this picture is one bubble among countless others. Eternal inflation is not a fringe idea. It is a natural consequence of most realistic inflationary models. Some of the founders of inflation, including Andre Linde and Alan Guth, take the eternal inflation picture seriously. The question is whether we can ever test it. By construction, the bubbles outside ours are causally disconnected from us. Light from them cannot reach us. Information cannot travel between them under normal circumstances. They are, in the strict sense, beyond observation. There is one exception. If two bubbles formed close enough together during the very early phase of inflation, they might have collided briefly before the inflating space between them grew too large. The collision would leave a mark on the cosmic microwave background, a circular cold spot, a directional alignment, a region of unusual structure. These are all things we have already seen in this story. Cosmologists have searched for bubble collision signatures in Planck data. Some teams have identified circular features that loosely match predictions. None have been confirmed at high statistical significance. The cold spot, in particular, has been suggested as a possible bubble collision scar, but the evidence is consistent with several other explanations. What eternal inflation contributes to the question of what came before is a specific framework. In this picture, our universe is not the first thing that ever happened. It is one bubble in an endlessly inflating background. Other bubbles existed before ours. Other bubbles will exist after. The phrase before is tricky here. The bubbles do not share a common time. Each one has its own history. But in the sense that some bubbles formed earlier in the total history of eternal inflation, yes, there were universes before ours. Some of those universes may have lasted only briefly. Some may still be active. Some may have produced observers who, like us, looked at their cosmic microwave background and wondered what came before. If eternal inflation is correct, the question is no longer whether anything existed before our universe. The question is what those other universes were like and whether any signature of contact with them is visible in our sky. There are signatures we can look for, specific kinds of marks, specific kinds of contact bruises. Some of them are exactly what the cold spot looks like. In 2011, a team of physicists led by Stephen Feeney at University College London performed a detailed search of WMAP data for signatures of bubble collisions. Their goal was not to prove the multiverse exists. Their goal was narrower. If our universe is part of an eternally inflating multiverse, and if our bubble collided with another bubble in its earliest moments, certain specific patterns should appear in the cosmic microwave background. They were looking for those patterns. The expected signature of a bubble collision is a circular feature with a specific temperature profile. The center of the circle would be the point of closest approach between the two bubbles. The radius would depend on the size and energy of the collision. The temperature pattern would either be slightly cooler or slightly warmer than the surrounding sky, depending on the dynamics. The Feeney team identified 4 candidate features in the WMAP data that loosely matched the predicted signature. They did not claim these features were definite collision marks. They claimed the candidates were worth following up with the more sensitive Planck data. When Planck released its results, the candidates were re-examined. The conclusion was that the features were consistent with statistical noise and did not require a bubble collision interpretation. No high-confidence detection has been made. The story does not end there. The cold spot, which we explored at the beginning of this script, has properties that match a bubble collision signature reasonably well. It is circular, it has a specific size, it has a temperature anomaly. Some teams have proposed that it could be a real collision scar. Others have argued that the supervoid plus a statistical fluctuation is enough to explain it. Without polarization data of sufficient quality, the two explanations cannot yet be cleanly distinguished. A future mission could change this. The proposed Lightbird satellite, planned for the 2030s, will measure the polarization of the cosmic microwave background to unprecedented precision. If the cold spot has a bubble collision origin, its polarization signature will be specific and distinguishable. If it has a more mundane origin, the polarization will be different. This is one of the rare cases where a metaphysical sounding question has a concrete observational test waiting in the near future. What makes the search for cosmic collisions important is not just the multiverse. It is the question of whether anything outside our universe has ever influenced what is inside it. If we can find evidence of even one collision, we will know the universe is not isolated. Other regions of reality exist. Some of them have touched ours. The implications cascade. If our universe collided with another in its first instant, then the conditions of that collision would have set initial conditions inside our universe. The smoothness, the temperature, the directional features in the cosmic microwave background could all carry imprints of what the other universe was like. Some of the anomalies we have been cataloging might be those imprints. In this sense, the cold spot is not just a curiosity. It is a candidate first contact event. We may have already detected the place where our universe touched another. We may already be staring at the only photograph we will ever have of a neighbor. The honest summary is that this is unconfirmed. The bubble collision interpretation of the cold spot is one of several. The case is suggestive, not proven. The deciding evidence is years away, but the search itself represents something remarkable. We have moved from theological speculation about other realms to scientific search for collision marks in our oldest light. We have specific predictions, specific tests, and specific instruments planned to perform those tests. If something existed beside us, we may find out. If something existed before us, the evidence may already be in our hands, waiting to be decoded. There is still one more line of evidence to consider. It is not about anomalies. It is about the laws of physics themselves. The fact that our universe operates by rules so finely tuned for stars, galaxies, and life that random origin starts to look impossible. That is the fine-tuning problem. And it forces another kind of question. The universe runs on a set of physical constants. The strength of gravity, the mass of the electron, the strength of the strong nuclear force, the cosmological constant that drives cosmic expansion. There are about 30 such numbers in total. Together, they define how reality behaves. Each one could, in principle, take any value. Physics does not tell us why gravity is the strength it is. It does not tell us why the electron has the mass it has. The numbers are inputs to the equations, not outputs. When physicists examine these inputs carefully, a strange pattern appears. The values are exactly what they need to be for stars to form, for atoms to be stable, for chemistry to work, and for life to be possible. If the strength of gravity were slightly different, stars would either burn out too quickly or never ignite. If the cosmological constant were larger, the universe would have expanded so rapidly that no structure could form. If the strong nuclear force was slightly weaker, atomic nuclei would not hold together. If the mass of the proton was slightly different, hydrogen would be unstable. The constants sit, in many cases, at the precise values needed for a universe like ours to exist. This is the fine-tuning problem, and it is real. The math of our universe is balanced on a knife's edge in several independent dimensions at once. There are three main responses. The first is to argue that the fine-tuning is an illusion. Maybe a deeper theory will eventually explain why the constants have the values they do. Maybe they are not really free parameters at all. Maybe some unknown principle fixes them. This is the hopeful position. It is also the least supported by current physics. Decades of theoretical work have not produced such a principle. The second is to invoke the multiverse. If many universes exist with different values of the constants, then most universes are dead. They cannot form stars. They cannot support chemistry. They contain no observers. We exist in this universe because we could only ever have evolved in a universe whose constants permitted us. The fine-tuning is selection bias. We are the rare universe that worked. This is the anthropic answer. It is widely discussed. It is also philosophically unsatisfying to many physicists, because it does not predict anything we can test. It just explains why we are here in the universe we are in. The third response is more interesting in the context of this script. The constants might have been set by whatever existed before our universe. In some pre-Big Bang models, the values of the constants are not random. They are determined by the conditions of the previous cosmos, transmitted through whatever transition produced our universe. In Penrose's conformal cyclic cosmology, the constants of one aeon might be inherited from the previous one. In bouncing universe models, the constants might be slowly drifting as the universe cycles through bounces, eventually settling into life-permitting ranges. In the ekpyrotic model, the constants depend on the geometry of the higher dimensional space and the conditions at the moment of membrane collision. Different collisions produce different universes with different constants. In each of these pictures, fine-tuning is not coincidence and not selection bias. It is consequence. The constants have the values they have because of what happened before. This is speculative. It is also a serious response to one of the deepest puzzles in physics. It says that the question of what came before is not just academic. It is the question of why our universe operates the way it does. If something existed before us, and if that something set the rules of our reality, then everything that follows from those rules, including stars, chemistry, biology, and us, can ultimately be traced back to its origin point, not to the Big Bang, to whatever produced the Big Bang. That is a striking thought. It is also one that some physicists take to its logical extreme. They ask whether the universe might not be a natural object at all, whether it might be running on a set of rules that have a different kind of origin entirely. The simulation hypothesis is a fringe idea taken seriously by a non-trivial number of serious physicists. It deserves a careful look. In 2003, philosopher Nick Bostrom published a paper arguing that, under specific assumptions, we are statistically more likely to be living in a computer simulation than in a base reality. His argument is logical, not physical. It states that if any civilization ever develops the technology to run extremely detailed simulations of conscious beings, and if any such civilization actually does so, then the number of simulated minds will eventually outnumber the number of biological minds. Any randomly selected mind, including yours, would more likely be simulated than not. The argument depends on several assumptions, each of which can be debated. But it is not absurd. It is taken seriously enough that some physicists, have asked whether the hypothesis could be tested. The answer is, surprisingly, maybe. If the universe is being simulated, the simulation must run on a computational substrate of some kind. That substrate, like any computer, has finite resolution. There would be a smallest unit of space, a smallest unit of time, a discreteness underlying what looks continuous. If we could detect that discreteness, we would have evidence that the universe is computational rather than continuous. In 2012, a team led by physicist Silas Bean at the University of Bonn proposed that high-energy cosmic rays might carry such evidence. Cosmic rays interact with a hypothetical underlying lattice of space-time in specific ways. The spectrum of the highest energy cosmic rays could show subtle distortions if the lattice exists. The team analyzed available data and found no clear signal. The result did not prove the simulation hypothesis. It also did not rule it out at the highest energies, where data is sparse. Other physicists have proposed different tests. Some look for unusual symmetries in particle physics that would emerge from a computational substrate. Some look for limits on information density in the universe. None have produced a confirmed signal. The honest summary is that the simulation hypothesis remains untested. It may be untestable in principle, since a sufficiently sophisticated simulation could hide its own existence. It is treated by most physicists as philosophy rather than science. It is included in this script for a specific reason. It represents a particular answer to the question of what existed before our universe. If we are in a simulation, then what existed before our universe is the system running the simulation. That system has its own physics, its own history, its own time. Our Big Bang might be the moment the program started. Our cosmic constants might be the parameters set by the programmers. Our anomalies might be glitches, or features, or deliberate signatures. This sounds outlandish. It is. But notice that it is structurally similar to other answers we have explored. In Penrose's cyclic cosmology, our universe was set up by the previous one. In bouncing models, by the contracted state of an earlier cosmos. In the ekpyrotic model, by the collision of two membranes. In eternal inflation, by the inflationary background that produced our bubble. Each of these answers says the same thing. Our universe is not the original. There was a system before it. That system set the conditions under which we now exist. The simulation hypothesis just adds one more variant. The system before is not another natural cosmos, but an engineered computational environment. Most physicists do not take the simulation hypothesis seriously enough to spend time on it. A few do. Among those who do, the question is not whether we live in a simulation. It is whether the question is even well-defined enough to be answered with physics. What unites all of these proposals is a single observation. Our universe shows signs of having been set up. Fine-tuned constants, anomalous initial conditions, order at scales that random origin cannot easily produce. Whatever set it up, whether a previous aeon, a previous cosmos, a higher dimensional collision, or a computational system, exists outside the framework we can directly observe. The honest scientific position is this: we cannot currently distinguish between these options. The evidence is suggestive of inheritance. The mechanism of inheritance is not yet identified. There is one specific version of inheritance that has gained traction in recent years. It is mathematically clean, observationally motivated, and quietly disturbing. Our universe may have been born inside a black hole that belongs to a different universe. In 1972, physicist Raj Pathria proposed an idea that has refused to go away. He argued that the observable universe satisfies the mathematical conditions for being the interior of a black hole. If you take the total mass of the observable universe and calculate the radius of a black hole with that mass, the answer is approximately the same as the size of the observable universe. The two numbers are within an order of magnitude of each other. This is suggestive. It is not proof, but it is striking enough to have generated a serious line of research. The black hole genesis hypothesis says that our universe is the interior of a black hole that exists in a different, larger universe. When matter fell into that black hole, it was compressed beyond a critical density and triggered a new inflationary phase. From the outside, the parent universe sees only a black hole. From the inside, observers like us see an expanding cosmos. The Big Bang in this picture is what black hole formation looks like from the inside. Several physicists have developed this idea. Lee Smolin proposed in 1992 that black hole formation could produce new universes through a related mechanism. He went further and proposed that universes could undergo a kind of natural selection. Universes whose physical constants favored black hole formation would produce more daughter universes, and over many generations, the constants would evolve toward values that maximize black hole production. Our universe, with its many black holes and its observed physical constants, fits this picture reasonably well. In 2024, a study by physicist Enrique Gastañaga and his colleagues argued for a more rigorous version of the black hole genesis idea. They showed that, under specific assumptions about the mathematics of bounce cosmology, the universe would naturally appear from the inside to have started with a Big Bang. The bounce occurs inside the gravitational collapse of a region of a larger cosmos. The end result, for observers inside, is exactly what we see. The hypothesis has not been confirmed. It is consistent with several lines of evidence, including the mass-radius coincidence, the smooth initial conditions, and the apparent fine-tuning of constants for structure formation. It also makes specific predictions, some of which involve subtle features in the cosmic microwave background that future observations may be able to test. What the hypothesis offers is an answer to a deep question. Why does our universe look the way it does? Why are the conditions so specific? Why is everything so well organized for galaxies and chemistry? In the black hole genesis picture, the answer is that our universe was formed by a process that selects for these conditions. The interior of a black hole, by its nature, produces a hot, dense, expanding region. That region cools, structures form, and over billions of years, observers emerge. Those observers, like us, look at their cosmic microwave background and see signs of inheritance. They see fine-tuning. They see anomalies. They see hints that something existed before. The something that existed before is the parent universe. Our reality in this picture is nested inside another. The black hole that birthed us is, from outside, just one of many. From inside is everything we can see. This is speculative. It is also one of the more mathematically supported speculative ideas. It does not require new physics beyond what is already needed for bounce cosmology. It is a natural extension of ideas that several mainstream physicists work on. The implication is one of the strangest in modern science. Our universe might be a single bubble of hot density inside the gravitational collapse of a region in another universe. The other universe might be vast, ancient, and unaware of us. Or it might be inhabited, and its inhabitants might be doing the same kind of cosmology we are doing, looking for signs of their own parent universe. The recursion has no obvious end. There is one feature of black holes that complicates this picture in an interesting way. Black holes do not just have an inside and an outside, they have memory. They store information about everything that has ever fallen into them. And that memory, by some interpretations, is what allows information from before to survive into the present. Black holes were once thought to be perfect erasers. Anything that fell in was gone. Mass, energy, and information all disappeared behind the event horizon, never to be recovered. In 1974, Stephen Hawking showed that black holes radiate. Through quantum effects near the event horizon, they slowly leak energy in the form of what is now called Hawking radiation. Over enormous timescales, they evaporate. Here is where the paradox arises. The radiation Hawking calculated is thermal. It contains no information about what fell into the black hole. If the black hole evaporates completely, the information is gone. But quantum mechanics says information cannot be destroyed. every quantum state must, in principle, be recoverable from later states. The paradox is this: either Hawking radiation is hiding information, or quantum mechanics is wrong. Both options have profound implications. For decades, physicists have debated which way to resolve the paradox. The current consensus, supported by string theory calculations and by recent work on what is called the page curve, is that information is preserved. It comes out in the radiation, encoded in subtle correlations that take careful analysis to extract. This is more than a technical point. It says that black holes do not erase the past. They store it. Everything that has ever fallen into a black hole, including information about the universe at the time it fell, is still encoded in the radiation that black hole eventually emits. If a black hole has been around long enough to fully evaporate, the radiation it produces carries the imprint of everything that ever entered it. Connect this to the question of what came before. In Penrose's conformal cyclic cosmology, supermassive black holes from the previous aeon spent unimaginable lengths of time evaporating. Their final flashes carry information about everything they ever consumed during the previous universe. If even a fraction of that radiation passes through the conformal handshake into our cosmic microwave background, then our oldest light contains information from a previous universe, encoded in a way we have not yet learned to read. The Hawking points we discussed in Chapter 8 would, in this picture, be more than thermal afterglow. They would be data, rich, complex, time-resolved data about the histories of supermassive black holes that finished their lives in the previous cosmos. Each one would contain compressed information about everything those black holes had ever experienced. We do not know how to decode that information. We may never know. The encoding involves quantum correlations far beyond what any current technology can measure. But the information, if Penrose is right, and if information preservation in black holes is correct, is there. This idea applies more broadly. In any model where universes inherit conditions from previous cosmoses, and where black holes preserve information, there is in principle a way to access deep past data. It would be encoded in the specific patterns of inherited features. The cold spot, the axis of evil, the asymmetries, the anomalies, would all be carriers of information from before. The question is whether the information can be extracted. The honest answer is that we do not know yet. We are still learning to read the cosmic microwave background as anything more than a smooth backdrop with small ripples. But the principle is now established. Information is not destroyed. It survives. Even through processes as extreme as black hole evaporation, even through transitions as radical as cosmological bounces or conformal handshakes, the universe carries its history with it. What this means for the larger question is striking. If something existed before our universe, the evidence is not necessarily lost. It is harder to read, but it has not been erased. The traces are still here, in the oldest light, in the largest structures, in the unexplained anomalies that keep showing up. We just do not yet know how to read them. There is one more signal worth examining before we close this story. It is not from the deep cosmic microwave background. It is from a specific moment in the history of the universe, roughly 180 million years after the Big Bang, the moment when the first stars turned on, and the signal we found there required new physics. In 2018, a small team of astronomers operating an antenna in the Australian outback announced a result that shook the cosmology community. The experiment was called EDGES, short for Experiment to Detect the Global Epoch of Reionization Signature. The goal was simple in concept and brutally difficult in practice. They were trying to detect the faint radio signal produced when the first stars in the universe turned on. The first stars are believed to have ignited around 180 million years after the Big Bang. Before they appeared, the universe was filled with neutral hydrogen gas at a specific temperature. When the first stars began radiating ultraviolet light, they altered the hydrogen in a measurable way. The hydrogen absorbed certain wavelengths of cosmic background radiation, leaving a faint dip in the radio sky at a specific frequency. This dip is the signature of cosmic dawn. It had never been detected before edges. The team spent years isolating their antenna from terrestrial radio interference, calibrating their instruments, and analyzing data. When they finally announced their result, the signal was there. Cosmic dawn had been detected, but the signal was wrong. It was about twice as deep as the standard cosmological model predicted. The dip in the radio sky was much more pronounced than expected. The hydrogen at the time of cosmic dawn appeared to have been much colder than any standard physics could account for. Something had cooled the early hydrogen below the expected temperature. The standard model could not explain how. Several theories were proposed. The most straightforward was that the hydrogen had interacted with another form of matter that was even colder. Specifically, dark matter. If the dark matter and ordinary matter had a small electromagnetic interaction, dark matter could have absorbed energy from the hydrogen, cooling it. This proposal required dark matter to have a small electric charge. Most dark matter candidates do not. Adding the charge would mean introducing new physics. Other proposals involved unusual radiation backgrounds, exotic particle interactions, or modifications to the way ordinary cosmology evolved. None of them fit cleanly into the standard model. A second team, called SARUS, attempted to verify the edge's result with a different antenna and different methods. They reported a non-detection. Their data did not show the deep absorption signal that EDGES had reported. The discrepancy is unresolved. EDGES says the signal is there and is anomalous. SARAS says the signal cannot be confirmed. The two teams have published responses to each other's analyses. The community continues to investigate. What the EDGES result represents, even if it is eventually withdrawn, is a clear example of how cosmic dawn observations can probe physics beyond the standard model. The first stars are a window into the early universe. The conditions when they ignited carry information about everything that came before. If the EDGES signal is real, and if the cooling was caused by dark matter interactions, then the dark matter we have been discussing is interacting in ways the standard model does not include. It would carry information about its own origin. Its interaction with hydrogen would be a clue to physics we have not yet uncovered. If the cooling was caused by something else, like a stronger than expected radio background from before the first stars, then there was structure in the universe at very early times that no standard model produces. That structure would have to have come from somewhere. The natural candidates are the same ones we have been discussing all along. New physics, or inheritance from before. The EDGES story is unfinished. The cosmic dawn signal will eventually be measured definitively by experiments like the Square Kilometre Array and the Hydrogen Epoch of Reionization Array. When it is, we will know whether the universe at the moment of first light was in a state our models predict, or in a state that requires explanation from beyond. Either way, the moment of first light is one of the deepest accessible probes of cosmic origin. It is the closest we can get to seeing the universe before stars, before galaxies, before the structure we now take for granted. It is also one of the last frontiers in this search. After 32 chapters of evidence, we are ready to ask the question that has been quietly building. What does all of this mean? And what does it tell us about whether something really existed before us? We have walked through 32 chapters of evidence, the cosmic microwave background and its anomalies, pre-Big Bang theories and their predictions, JWST galaxies that should not exist, Hubble tensions and possible age miscalculations, primordial black holes and dark matter, structures larger than the cosmological principle allows, bubble universes and cosmic collisions, fine-tuning, simulations, black hole genesis, information paradoxes, and the strange signal at cosmic dawn. No single piece of this evidence proves that something existed before our universe. Most of it is suggestive. Some of it is contested. A few items are genuinely controversial within the scientific community. What the evidence does, taken together, is force a reconsideration of the simple story. The simple story says the universe began at the Big Bang. Time started, space started, there was no before. The question of what came earlier is meaningless, because there was no earlier in which it could have happened. This story has held up for decades. It is internally consistent. It fits much of the data. It is also showing signs of strain. The strain comes from multiple directions. Anomalies in the cosmic microwave background that point to directional features the standard model does not predict. Galaxies that appear too mature for the timeline. Measurement disagreements about the expansion rate that cannot be resolved within the current framework. Structures so large that they violate the cosmological principle, a possibility that the universe is older than 13.8 billion years. Particles like sterile neutrinos that almost show up. Element abundances that do not match. A signal at cosmic dawn that may require new physics. Black holes whose information must be preserved. Constants of nature so finely tuned that random origin becomes statistically untenable. None of these alone is fatal to the simple story. All of them together suggest the simple story is incomplete. The candidate replacements share a common feature. They invoke something before our universe. That something can take many forms. A previous aeon that handed off its smooth final state to ours. A contracted cosmos that bounced into the current expansion. A higher dimensional collision that ignited reality. An eternally inflating multiverse in which our bubble is one of many. A parent universe that produced ours through black hole genesis. A computational substrate that runs the simulation. Or some combination of these. We cannot currently distinguish between most of these options. The data is suggestive, not decisive. The next decade of observations, particularly from missions like Lightbird, the Square Kilometre Array, the Roman Space Telescope, and follow-up Webb observations, will tighten the constraints. Some scenarios will be ruled out, others will gain support, some new ones will emerge. What is no longer in serious doubt is that the question has become scientific. For most of human history, asking what came before the universe was a question for theology or philosophy. It was outside the reach of empirical investigation. There was no way to test any answer. The question was real, but the methods to address it did not exist. That has changed. We now have detailed observations of the oldest light. We have gravitational wave detectors that can probe the structure of space-time at extreme densities. We have telescopes capable of seeing galaxies a few 100 million years after the Big Bang. We have nuclear physics experiments that probe what happened in the first 3 minutes. We have theoretical frameworks, like loop quantum gravity and conformal cyclic cosmology, that make specific predictions about events before the conventional beginning. The question is no longer whether we can investigate what existed before. The question is what the investigation will eventually reveal. The honest answer today is that we do not yet know. The pattern of anomalies is real. The pre-Big Bang frameworks are credible. The decisive evidence is not yet in hand. Anyone who tells you with certainty that they know what came before our universe is either ahead of the data or making something up. But the evidence we do have leans in one direction. The smoothness of the early universe is too perfect to be random. The fine-tuning of constants is too precise to be accidental. The anomalies in the cosmic microwave background are too persistent to be flukes. The structures we are finding are too large for the standard timeline. Something gave our universe its starting conditions. That something operated before the conditions we observe. What it was, we are still learning. But it was not nothing. Something existed here before us. The evidence is in the oldest light, in the largest structures, in the smallest particles, in the quieter signals from the first stars. It is in the math of physicists who refuse to stop at the singularity. It is in the data of telescopes that keep finding more than they should. We are looking at the traces of a universe that was here before ours was. We do not know its name. We do not know its shape. We do not know what ended it or what began it. We only know that we are not the first, and we are still listening.